Kak Akmaliza. Today I'm going to present an introduction part of our report. The heat of solution is the difference in a heat energy when a solute is dissolved in a solvent such as water. The difference in energy may be endothermic, that heat absorbing, or exothermic, heat releasing, depending upon the nature of the solute and the intermolecular forces between the solvent particles and the solute particles. The concentration of the solute is a principal factor in dictating the quantity of heat utilized throughout the dissolving process. As concentration is raised, the number of particles of the solute that engage the solvent also becomes altered, potentially affecting the total heat released or absorbed. For purpose of this study, sodium chloride and HCl is utilized as the solute. NaCl, when dissolved in water, dissociate into sodium Na+ and chloride Cl- ions. This is a dissociation process of the ionic bonds in the solid and establishment of new forces between the ions and water molecules. For NaCl, the solution process is slightly endothermic as it absorbs a small amount of heat from the surroundings. The temperature of the solution can drop a little by this process. The aim of the experiment is to investigate how different concentration of NaCl affect the heat of solution. Next part is the research problem. The first problem is this study investigates how change in solute concentration affect the heat of solution during the dissolution of NaCl in water. X, although NaCl dissolves endothermically, the effect of its concentration on heat absorption is not clearly known, so this study explores that relationship. Plus, since NaCl concentration may influence solution temperature, this study aims to examine its effect on the heat of solution for better control in practical application.
Hello everyone, my name is Tadishan, matrix number BS2311016, and now I would like to introduce the objective of this report. So the first objective is to evaluate the effect of sodium chloride concentration on its heat of solution in water by reviewing existing literature and theoretical models. The second objective is to identify the trends and thermodynamic principles that explaining concentration effect. And now we are going to the hypothesis of this report. So the hypothesis states that the higher the concentration of sodium chloride will decrease the heat of solution in water due to the reduced solvation energy from increased ion interactions.
Hi, my name is Peter Sakwichi, number matrix BS2311090, and I will be presenting literature review for this mini project. This review takes a close look at the effects of solute concentration on heat of solution and highlight main results from studies in the field. The quantity of heat in a solution depends on connection between solutes, between solvents, and between solutes and solvent. Under Hess law, the overall enthalpy change equal in energy involved in breaking solutes and solvents bond together with the energy for forming this same solute-solvent interaction. When the amount of solute in solution rises, the nature of this interaction changes, and so does the final heat affected. There are some experimental studies for this topic. First, the study of Atkins and De Paula 2014 suggested that for solution of sodium chloride, the heat released during solution change as the concentration does, because ion pairing and activity coefficient change. Number 2, Smith 2010 investigated the dilution of urea in water and found that the heat of dissolution decreases when more urea is added. Number 3, CRC Handbook of Chemistry and Physics reveals that for several solutes, their heat of solution change and does not remain constant as concentration change. There are some thermodynamic models for this topic also. First, the Hacker and Pitzer models. The models are designed to include ionic interaction effects over a range of ion concentrations. The results indicate that heat of solution depends strongly on the concentration because of both ionic strength and the pairing of particular ions. Number 2, molecular dynamics simulations. This model uses simulations to track change in heat flow as solute dissolve. This simulation confirms that as solute concentration increases, disruption of solvent structure and accumulation of solute cluster reduce the magnitude of enthalpy change.
Good day everyone, my name is Ong. Now I would like to present the discussion part. So for interpretation of the results, as the concentration of NaCl increased, the temperature change decreased, indicating a diminishing enthalpy effect per gram or mole of solute. This aligns with the idea that NaCl dissolves in water with a slightly endothermic heat of solution. Next, the value of delta H is positive but small, around positive 3.9 kJ per mole. However, the trend suggests an interesting nuance, which at low concentration, the solution seems to involve a more noticeable temperature change, while at higher concentrations, the temperature either remains steady or increases only slightly. Next, I'll suggest some factors and effects of this situation. So firstly, saturation and ion interaction effects. At lower concentrations, NaCl dissociates readily into Na+ and Cl- ions, and water molecules have sufficient freedom to salvage these ions effectively. But as the concentration increases, ion crowding becomes a factor. More ions in the solution lead to inter-ionic interactions, which are ion pairing or clustering, which then reduce the net energy change. Next is salvation shell overlap starts happening. Water molecules get used up around other ions, so new solvation becomes less efficient. Secondly is thermodynamic interpretation. The trend also points to an important thermodynamic principle where delta H solution is not constant across concentrations. Although it often presents as a fixed value, in reality it depends on the state of the solute like crystalline, hydrated, and etc., the degree of dilution, and the interactions between solute and solvent molecules.
Now, let's move on to the applications. First, improves process control in industrial applications. Knowing how solute concentrations affect heat during dissolving helps industries like chemical manufacturing, food processing, and pharmaceuticals control temperature better. Example, when making saline solutions, understanding heat change can prevent unwanted temperature shift that may harm active ingredients. Second, optimizing energy usage and mixing and solutions. In systems like reactors or calorimeters, knowing if a solute absorbs or releases heat at certain concentrations helps reduce energy waste. If it absorbs more heat at low concentrations, engineers can adjust energy output to match. 3. Impact on solubility and reaction speed. Heat of solutions affect how fast solute dissolve. For example, in tablet productions, endothermic drugs may dissolve slower at high concentrations unless heat is added, affecting how well the medicine works. This study shows that the amount of sodium chloride NaCl in water affects how much heat is involved when it dissolves. At low concentrations, there is a clear temperature change, showing a slightly endothermic process, but at higher concentrations, the temperature change becomes smaller or even disappears. This happens because of things like ion crowding, reduced solvation ability, and water reaching its limit to strong new ions. So, the heat of solutions is not always the same. It changes with dilution's physical state and how the solute interacts with the solvent. These studies help us better understand how the solving works and give us useful insight for both science and industry. That's all from us. Thank you.